Today we're going to talk about interval notation because you're often going to be asked to tell us the domain or where a certain function is continuous or where it's differentiable, and you'll be asked to do that by giving it an interval notation. I am going to post that little link to the survey again, just in case somebody needs it. Okay, so let's talk about interval notation. The main thing is if the endpoints are included, it gets a square bracket. If the endpoints are excluded, it gets a parenthesis. So if you had a picture, a square bracket would be equivalent to a closed dot, and a parenthesis would be equivalent to an open dot. Infinity and negative infinity will always get parentheses because we can't get there. You can't include infinity. So one of the most common things we have to write is all real numbers. And that just means everybody from negative infinity to infinity. Often we're asked for the domain of a rational function, which is everything except where the denominator is equal to 0. So every number except, say, -4 and 4. So then it would be everybody less than -4, everybody between -4 and 4, and everything bigger than +4. Excuse me. So if it's everything except these two numbers, then we have these two little union symbols to represent where those numbers live. That kind of helps me to make sure I have everything the way it should be. So far, so good?
Yes.
Now, if you were asked for the domain of a square root function, say x minus 2. Well, we can't take the square root of anything negative. So x minus 2 would need to be greater than or equal to 0. So x would need to be greater than or equal to 2. So in interval notation, the or equal to means square brackets all the way up to infinity. If we were asked for the domain of a logarithmic function, something like the natural log of x minus 2, we can only take the natural log of positive stuff. So that means x minus 2 has to be strictly greater than 0. So x would have to be strictly greater than 2, and in interval notation, that would be 2 to infinity. Sometimes you'll have to go from a picture. So I'm going to make this picture a little bigger because my vision's not that good. So this one, we have a closed dot here at the left end, and it happens to be at -1. So it gets a square bracket. All of the x values are included. We have this open dot here at 4, but this dot here at 4, 1 is closed, so it's not left out. We include everybody up to, but not including 7. So a lot of students want to do -1 to 4 and then 4 to 7. That's not necessary because that 4 is included in this piece. And my last little example here, the fact that it's going off the page implies that it starts at -infinity. Now we have an open circle and it jumps down to another open circle. So 2 is left out. We have everything from 2 to 4, and then it jumps up here, but we have a closed circle, so we don't have to leave 4 out. We get all the way to 5 before we have anybody left out, and then everything from 5 to forever. So just a quick little review of interval notation. Any questions? If you want more practice, there's the math is fun. Makes sense. Awesome. Hopefully you all got your copies of the worksheets. I just sent an email right before the workshop started, so you should have copies, your very own copies of the worksheets. If not, let me know. Shoot me an email and I'll send them to you. All righty. Let's go on to the next topic, which is simplifying rational expressions. And we're going to go through 3 different types of simplifying rational expressions. And you've probably seen some of these already in doing your limit problems. So we'll start where we can just factor the numerator, factor the denominator, and cancel stuff. And I start with this one that looks really simple. We have x minus 5 on top and 5 minus x on the bottom, and we really, really want to be able to cancel something because they look so much alike that we must be able to cancel. But remember, in order to cancel, you have to have exact same factor on the top as on the bottom. It's not quite exactly alike, but I could factor a -1 out here, and I would have negative x plus 5 over 5 minus x. And generally, when I start canceling stuff like factoring stuff like that, I like to make sure that I haven't changed anything. So I'm going to multiply back through. Negative times negative gives me positive. Negative times positive gives me negative. So indeed, it is the exact same thing. Well, this is the same as 5 minus x over 5 minus x. Now I can cancel that away, and I'm left with just a -1. Now I put all those steps in just to make it really, really clear what's going on. You wouldn't have to show all those steps in your work. Just be careful and know that you have to factor that -1 out before you can cancel stuff. You'll see that one a lot. Okay, next one, we're just going to factor the numerator, factor the denominator, and hope we get to cancel something. Difference of 2 squares. Two numbers whose product is -2, whose sum is -1. -2 plus 1. Oh, and now I'm really happy. I get to cancel, and it's one of my favorite things to do. And I'm left with just x plus 2 on top of x plus 1. Now you see this one a lot when you have one of those limits where you end up with 0 on top of 0, and then you try to factor and see if something will cancel away. Next one, I have x cubed plus 2x squared minus 15x. All of that living on top of x to the 4th minus 81. So first thing you do when you have something to factor is look for common factors. Everybody up top has an x. So I'm going to pull x out. X squared plus 2x minus 15. Then down below, I think about the fact that any even exponent can be written as x squared squared. So if I had x to the 6th power, I could write it as x cubed squared, because when you have a power raised to a power, you just multiply. So this is another difference of two squares. I have x squared minus 9 times x squared plus 9. Now from there, I'm going to factor some more, because the numerator, I have two numbers whose product is negative 15, whose sum is positive 2, plus 5, minus 3 will work. Down below, I can factor x squared minus 9, again a difference of two squares, x minus 3 times x plus 3. And even though it's very, very disappointing, x squared plus 9 does not factor. No matter how hard you try, if you are in the real world with real numbers, x squared plus 9 does not factor. Questions? And we get to cancel just one thing. Okay, cool. I got to make sense. All righty.
I have a question.
Okay.
Can you not factor the x squared plus 9?
You cannot. I know, it's so simple, and it looks like you should be able to factor that doggone thing. But think about it, you would need two numbers whose product is equal to 9, whose sum is equal to 0. Because remember, that's how we factor things. We plop an x down here, we plop an x down there, and then we look at this number here and we think, okay, well, I need a 9 to come out. So that means it's either 9 and 1 or 3 and 3. If I put 3 there and 3 there, well, I need a positive 9, so it would either have to be minus 3 and minus 3, or it would have to be x plus 3 times x plus 3. So what would I get if I FOILed out x plus 3 times x plus 3? First, outer, inner, last. If I tried it with the minus sign, I'd end up with minus 6x in the middle. The only reason it works with a difference of two squares is because I can have a plus and a minus and the middle falls out.
Okay, I see. Thanks.
You're welcome. And I was just grading quizzes in my Calc 2 class, and some of them made that exact same error. They tried to factor x squared plus 9 as x plus 3 times x plus 3. So it's a very common mistake. Everybody wants to do it. It looks like something that should factor, but it's not. Okay, next thing is when we have a fraction over a fraction. So a rational expression on top of a rational expression. And the way we take care of that is by multiplying by 1 in a strange way that allows us to cancel stuff. We multiply by the least common denominator divided by the least common denominator. So I'm going to start with this special one, where I only have one term sitting on top of one term. Now, this one you can use a little shortcut on. Instead of having to multiply by the least common denominator, you can just rewrite this as a division problem. So, who remembers how fraction division works? You multiply by what?
Do you switch like the bottom denominator, like 3x minus 1 will go on top, and 3 minus 4x squared will go on the bottom, and you multiply it?
Perfect. You invert and multiply. You multiply by the reciprocal. You write down the numerator and multiply by the bottom flipped upside down. Oh, well, yeah, we're done. We can just combine that into one unit. Which is super easy when we just have one little fraction on top of one little fraction. But we often have something that looks more like the next example here. 1 over x plus h minus 1 over x minus 1. You'll be seeing things like this next week when you start talking about the limit definition of the derivative. We'll need to simplify this thing. So we find the least common denominator of all of our rational expressions. So between 1 over x plus h minus 1 and 1 over x minus 1. Well, my least common denominator has to have both of those denominators in it because they don't have any factors in common. So I'm going to multiply numerator and denominator by least common denominator over least common denominator. So I do it to the top and I do it to the bottom. I haven't changed anything. I just multiplied by 1 in a very unusual way. Now in the denominator, don't combine anything. Just leave it the way it is. Up top, I'm going to distribute. And again, the bottom is staying exactly the way it is. X plus h minus 1, x minus 1. Now comes my favorite part, where I get to cancel stuff. Oops, I canceled the wrong thing. That one stays. That cancels, and that cancels. Be very careful with the parentheses. So I'm going to take another row just to get rid of those parentheses in the numerator. Well, this set of parentheses isn't doing anything. But this one says that everybody inside deserves a brand new sign. So x gets a brand new sign, h gets a brand new sign, -1 gets a brand new sign. X minus x goes away. -1 plus 1 goes away. And I'm left with a negative h sitting on top of h times x plus h minus 1 times x minus 1. Oh boy, I get to cancel again because I have an h on top and an h on the bottom. And I end up with -1 on top of this times that. Questions? So again, it's going to come in handy next week. Last one we're going to talk about for simplifying rational expressions. You've probably seen already when you were doing your limits that had square roots in them. It's multiplying by the conjugate of a radical expression, which means the exact same terms with the opposite sign in between. And the reason we do it is because it makes magical things happen. It makes the radical disappear. So something like 5 minus the square root of x over 25x minus x squared. So I want to make the square root disappear. I'll multiply by 5 plus square root of x over 5 plus square root of x. So I'll FOIL again, because anytime you have two terms multiplied together, it's going to be foiling. You have to be sure you FOIL so you don't forget to multiply anybody by anybody else. So first times first gives me 25. Outers gives me plus 5 times the square root of x. Inners gives me minus 5 times the square root of x. And last gives me negative times positive is minus square root of x times square root of x is x. Well, while I'm at it, I'm going to go ahead and factor this because everybody's got an x. So I have 25 minus x and then 5 plus the square root of x. 5 root of x minus 5 root of x goes away just like I planned it. That was the whole purpose in multiplying by that conjugate. And now down below, I'm left with 25 minus x times 5 plus the square root of x. Oh, look at that. I get to cancel again. I'm so happy. And I end up with just 1 sitting on top of 5 plus the square root of x. Questions? So you've probably seen this before, and students struggle with it. Another thing is to just always be careful with your parentheses. And do another one. And get a whole new board because I write big. We have x over square root of 3 plus x minus square root of 3. 3 plus x. So exact same terms with the opposite sign sitting in the middle. That's going to make the middle fall out when I do the foiling. That's the whole purpose in multiplying by that conjugate. So up top, don't distribute that x. Leave it just the way it is. Down below, first outer inner last, we know our middle's going to fall out. So square root of 3x times square root of 3 plus x is 3 plus x. We have a minus times a plus, so it's minus. Square root of 3 times square root of 3 is just 3. So I have x times 3 plus 3, living on top of 3 plus x minus 3. 3 minus 3 goes away. And now that cancels with that. And boy, that's a lot simpler than what I started with. If you were taking a limit, that's something you could plug anything into that didn't give you a negative number underneath there. Questions? So somebody said this is a tough one for them. It's tough for everybody, and that's okay. It just takes practice, more and more practice.
Can we do another example like this, very similar?
Sure. I'll have to just make one up, but I can certainly do that. So we'll have x minus, let's see, make one where the parentheses are going to be important. So we'll do square root of x minus the square root of x plus 5 over x plus 5. I don't know if any fun canceling will happen because I haven't planned this one, but we'll still see the process of doing the multiplying by the conjugate. So I would multiply by square root of x plus square root of x plus 5 over square root of x plus square root of x plus 5. So when I multiply up top, I have square root of x times square root of x gives me x. If I did outers, I would get plus square root of x times square root of x plus 5. If I did inners, I'd get minus square root of x times square root of x plus 5, and they would just destroy one another. So now I have minus x plus 5, because I have minus times plus, minus there. Square root of x plus 5 times square root of x plus 5 just gives me x plus 5. And notice I put parentheses around it. because parentheses are important. I leave the bottom alone. Now I simplify the numerator as much as I can by getting rid of those parentheses. And now x minus x goes away, and I'm left with just a -5 on top. Yeah, no fun canceling happened, but we got to see another magical getting rid of the radical. It just moves the radical from one side of the fraction bar to the other, but generally that's our goal, is to simplify one side. Did that help?
Yes, it did. Thank you.
Good. Okay, leaves us with lots of time to talk about graphing rational expressions, rational functions. Now, you probably learned this back in pre-calculus 171 if you took it here at Wake Tech. But we're going to go over it because you've probably not been graphing rational expressions for fun for a while. So I'm going to start with, and I wrote them on some graph paper. There's my graph paper. First thing we're going to do is find the domain. And the way you find the domain of a rational function, it's everything except numbers that make the denominator equal to 0. So I take my denominator. This is a nice simple one. And I just set it not equal to 0. So x minus 4, actually it should be x plus 4. Let's make it the same as what I have written down on the page here. X plus 4 is not allowed to be equal to 0. So x is not allowed to be -4. And then the reason we went over interval notation, to write this in interval notation, it's everything less than -4 combined with everything bigger than -4. So I can plug anything in there except -4. Next one, finding the domain of x squared minus 9 over x squared minus 16. Well, I really like to factor, so I'm going to go ahead and factor the numerator. And I'm going to factor the denominator. Looking for the domain means that the denominator is not allowed to be 0 because denominators can never be 0. So x minus 4 times x plus 4 is not allowed to be 0. So x can't be 4. X can't be -4. In interval notation, everything between negative and +4, and everything bigger than 4. Be sure you write them in order. -4 comes first from left to right. And each of these excluded values is represented by one of the union symbols. So this one has 2 little holes in its domain. Next one. So Again, when you have a rational expression and you're going to graph it, go ahead and factor stuff. So let's factor the numerator. Every number there is even. So if every number is even, go ahead and factor that 2 out. And I'll go ahead and factor the denominator. 2 numbers whose product is -12, whose sum is -1. Well, since that's negative, the 4 gets to be negative, and the 3 gets to be positive. Looks like I can do a little more factoring up top. Two numbers whose product is 8, whose sum is -6. Well, since this one is positive, that means each factor has the same sign, and since this one's negative, that means they're both negative. So to get 8, I need 4 times 2. Now, I look at that and I see, ooh, I can cancel, and I'm really excited and I can't wait to cancel. But don't cancel before you figure out what your domain is. Get your domain before canceling. Because even though we can cancel that away, 4 is still not going to be part of the domain of this function. So x minus 4 times x plus 3 is not allowed to be equal to 0. X minus 4 can't be 0. X plus 3 cannot be 0. And again, interval notation, -infinity to -3, everything between -3 and 4, everything bigger than 4. And now, finally, let's look at this one. Oh, once again, we have a common factor up top. X squared plus 3x plus 2, living on top of x squared plus 1. Oh, we really, really want that to factor, but it doesn't, doggone it, because of the plus sign there. If there were a minus sign there, we could factor it. But since it's a plus sign, we would have to go into the imaginary world in order to factor it. And we are not going into the imaginary world today. So I simplified that numerator as much as I could. I take that denominator and I set it not equal to 0. Well, that's true everywhere. There is no number that you can plug in there, no real number that you can plug in there and get 0 to come out. So my domain is all real numbers. So finding domain of rational functions, pretty easy. Questions? Okay, next thing. Excuse me, little kitty, I need my paper. We're going to talk about is vertical asymptotes. Vertical asymptotes happen where the denominator is equal to 0 and you can't cancel the offending factor away. So, since x is equal to 0 at -4, That means x equals -4. You're gonna get over there, honey. Oh. Okay, what did you do? Okay, there we go. Sorry about that. My cat wanted to get in on the action. So x equals -4 is going to be the location of a vertical asymptote. Let's see if she closed down my paper. Yep, she did. Okay, that's all right. I can get it back again. Next one was x squared minus 9 over x squared minus 16. Nothing cancels here. So both of these -4 and +4 will both be the locations of vertical asymptotes. So I'm just going to say VA because I get tired of writing vertical asymptotes. So x equals -4 and x equals +4 are locations of vertical asymptotes. And let's see, next one is this one. Now, this is the special one because we notice we can cancel here. And I'm going to call this f simplified of x. So f simplified of x is equal to 2 times x minus 2 over x plus 3. It's what you get if you simplified that rational expression like we were doing in the previous examples. This function has the same graph as f of x, except when x is equal to 4, because that's what we canceled away. So at x equals 4, there is a hole in the graph. If you took the limit as x approached 4 of this original function, you would get a perfectly good answer. If you take the limit as x approaches -3 of this function, it will not exist because it has a vertical asymptote there. So x equals -3 is the location of this guy's vertical asymptote. Another interesting fact about a vertical asymptote, as long as your factor down here is raised to an odd power, which the invisible 1, which is the power of this one, is odd, that means that your graph is going to go up on one side and down on the other. The only way they'll go in the same direction is if you have a factor with an even exponent on it. So we know that it's going to go up on one side, positive infinity, to negative infinity on the other. It's going to switch directions. It's going to help when we're graphing these things. This one, since the denominator has no zeros, there are no vertical asymptotes. Okay, looks like Luna added a little something to my sheet here. We've done vertical asymptotes. Let's talk about horizontal asymptotes. When we're talking about horizontal asymptotes, we look at the degree of the numerator versus the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, then it's back to that old limit rule that we have about big bottoms going to 0. So the bottom's going to get bigger than the top. This one's going to go to 0. So your horizontal asymptote is equal to the x-axis. And the equation for the x-axis is y equals 0. If the degree of the numerator is exactly the same as the degree of the denominator, then your horizontal asymptote is the line y equals leading coefficient over leading coefficient. Those lead terms are large and in charge. They're growing at the same rate, so they approach leading coefficient over leading coefficient. If the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptotes. The ends behave like a polynomial. They behave like leading term over leading term. And we'll see an example of that. So we'll keep this by for reference. And we'll go back to that very first simplest example where we have just 1 over x plus 4. Degree of this numerator is 0. Degree of the denominator is 1. 0 is less than 1. That means the horizontal asymptote is y equals 0. Let me label this was my vertical asymptote. Vertical asymptotes always say x equals something. Horizontal asymptotes are always y equals something. So this one's approaching the x-axis. And the nice thing about rational functions is their horizontal asymptotes are the same on both sides, so you don't have to check positive infinity versus negative infinity. They're both the same. We can go back and look at the very beginning to check the degree of the numerator and the denominator. So degree of numerator equals degree of denominator equals 2. So my horizontal asymptote is y equals leading coefficient over leading coefficient, which is just y equals 1. Looking back at the tippy top of this one, once again, degree of numerator and degree of denominator are the same. So horizontal asymptote at y equals leading coefficient over leading coefficient. And remember, it's the leading coefficient when you write it in descending order of exponents. If I had written the 12 first, that would not make it the leading coefficient. You have to have them in descending order of exponents to give it the title leading coefficient. And now this one, degree of numerator is 3, which is greater than the degree of the denominator, which is 2. So not only does this one have no vertical asymptotes, he has no horizontal asymptotes either. He's just asymptoteless. No asymptotes for you, young man. But I know the end behavior is like leading term over leading term. Again, biggest exponent on top over biggest exponent on the bottom. So I know what its ends do. Its ends look like the identity line, y equals x. So it goes down to the left and up to the right, just like the identity line does. So as x approaches negative infinity, this graph approaches negative infinity. As x approaches positive infinity, this graph approaches positive infinity. Questions so far?
Yes, ma'am. Sorry, could you explain why the end behavior does that again? I wasn't like following like the leading coefficient over leading coefficient thing.
The reason that it does that is because as x gets really, really big, your leading terms are more powerful than anything else. They take over. So as x gets bigger and bigger and bigger, adding 2x to it, adding 3x squared to it has so little effect on x cubed that x cubed is in charge. As x gets bigger and bigger and bigger, adding 1 to x squared is so unimportant it doesn't matter. So by the time we get to really big numbers, this expression is going to look exactly the same as the expression without all that extra stuff on it. Does that make sense?
Yes, ma'am. Thank you.
Cool.
So is that only when it's like approaching infinity when you do that, or is that just like?
That's only approaching infinity. That's not approaching any other number.
Okay.
Yeah. That only works at infinity and negative infinity. Nowhere else. It only applies to what we call end behavior. What's happening as x gets really, really big or really, really small. Good question. Okay. Now we're going to finally draw these things. And I am not the best artist in the world, which is why I got some graph paper for myself. I have my ruler that belonged to my daughter when she was in elementary school. Make myself a set of axes. So first thing I do is I go with what I know. First thing we calculated was the domain. And the domain was everything except -4, and we have a vertical asymptote at -4. So at -4, I'm going to put in a dashed line to indicate that vertical asymptote. Next thing we calculated was my horizontal asymptote, and it's sitting right there on the x-axis when y equals 0. So I'm just going to add some little dashes at the end here to indicate as x gets bigger and bigger and bigger, and as x gets smaller and smaller and smaller, I have to approach the x-axis. Now, next thing I want to do is find any intercepts. To find the x-intercepts, we set the numerator equal to 0. Well, I can't do that here. 1 is never going to equal to 0, no matter how hard I try to make it. So there is no x-intercept. This function is not allowed to cross the x-axis anywhere. To find a y-intercept, I let x be equal to 0. So f of 0 is equal to 1 over 0 plus 4. So 1/4. I know the point 0, 1/4 is on my graph. So about right there. Now, I know everything I need to know to draw this graph now. It doesn't look like it because all I've got is a point and a bunch of dashed lines, but I really do, because as x approaches infinity, I have to get closer and closer to the x-axis. As x approaches the line x equals -4, I have to shoot off to either positive infinity or negative infinity. And since I'm not allowed to cross the x-axis, I have to go that way. Now, since I know I'm going this way on the right side of this asymptote, I have to go that way on the other side of the asymptote. Now, I've been drawing these graphs a long time, so I know how to do that. If you're doubtful, just take a point close to -4. So let x be equal to something a little bit bigger. So right over here, -3.9. If I plug -3.9 into my function, I get 1 over -3.9 plus 4, so 1 over 0.1. That's a positive thing. If I let x be equal to something over here on the other side of this asymptote, something like -4.1, f of -4.1 would be equal to 1 over -0.1. It would be a negative thing. So it's going to have to go to negative infinity over here and positive infinity over there. Questions? Besides, who knew it could be so easy to graph rational functions? Okay, let's look at the next one. Make myself a set of axes. So put in what you know. We know where those vertical asymptotes are. Vertical asymptotes at ±4. So ichi, ni, san, shi. 1, 2, 3, 4. And that's it. I can't count in any other languages. So x equals 4, x equals -4. Let's dash in the horizontal asymptote. Well, the horizontal asymptote is at y equals 1. So I just put those at the end because horizontal asymptotes tell me about end behavior. So I just put the little dashes there at the ends. Now I'm going to plot some points. We'll look at those intercepts. We let the numerator be equal to 0. You can go here to your prefactored form, or you could go here and look at x squared minus 9 equals 0. And think about the good old square root property. If x squared is equal to 9, then x is equal to plus or minus the square root of 9. So x is plus or minus 3. Don't forget the plus or minus. You lose half your answers if you forget the plus or minus. So we have negative 3, 0, and 3, 0 that live on our graph. So you and you. Now I let x be equal to 0. I like to go back to the very beginning because then it's really easy to plug 0 in. You just have to look at constant term over constant term. Negative 9 over 16 over negative 16. So negative over a negative is positive. So the point 0, 9 over 16. About right there. And again, I now know everything I need to know to draw my graph. I have to approach this asymptote. I have to approach this asymptote. Since I'm going down on that side, I got to go up on this side. And I have to approach the horizontal asymptote. And I'm not allowed to cross the x-axis anywhere else.
How do you know that you're going up on the other side again?
Because you'll always, unless you have a squared term down here, it's always going to go up on one side and down on the other.
Okay.
And that's because it changes signs there. If you think about, if you plug in a number less than 4 right here, something at less than negative 4, excuse me. So if you plug in something less than negative 4 into this term, it's going to be a negative thing. If you plug in something bigger than negative 4, it's going to be a positive thing. So this expression changes sign at negative 4, and then it changes sign again at positive 4.
Oh my gosh, that makes so much sense.
Isn't that cool?
The way you worded that, it really clicked. Oh my gosh.
Awesome. I love it when it clicks. And it's funny how you can say it in exactly the right way, and finally it makes sense why that works that way.
Makes so much more sense now. Oh my gosh.
Yeah, because it's where one of the zeros is. So it changes signs at 3. It changes signs at negative 3. It changes signs at all the zeros. Okay, looks like this is my next one. This is the one that has a hole. So we get to plot the hole. Okay, so vertical asymptote. We had a vertical asymptote at negative 3. But 4 is also not in the domain of this function. So I have to deal with that. It's the location of a hole. So to find the place where the hole is, we have to take 4 and plug it into this simplified thing. So f simplified, evaluated at 4, would be equal to 2 times 4 minus 2 over 4 plus 3, which would be 2 times 2 over 7, 4 over 7. So when x is equal to 4, 1, 2, 3, 4, we're here less than 1, somewhere close to a half, a little bit more than a half. And I draw a circle there because it's left out. It's not in the domain. There's a hole there. Now, everywhere else, my function looks exactly like this guy. So I don't have to go back to the original guy to find my x and my y intercepts. I can use this simplified version to find my x and y intercepts. So I'll set this numerator equal to 0. I know the point 2, 0 is on my graph. And before I go any further, I'm going to dash in my horizontal asymptote at 2 because I don't want to forget about it. Okay, so I have the x-intercept. The y-intercept is when this thing evaluated at x equals 0. Then I have 2 times 0 minus 2 over 0 plus 3 gives me negative 4 over 3. So right about here. I'm ready to graph because I have to play connect the dots. Even the open dots, they have to be connected too. I have to approach that asymptote. And again, it changes signs when x gets less than negative 3, so it pops up here above the axis, above the asymptote, because it's not allowed to cross that axis ever again. It has to stay above it. Questions? Okay, we get this last one. This one's kind of funny looking. It has no asymptotes. Its domain is all real numbers. So what do I know about it? The only thing I was able to discover was its end behavior. Its end behavior is like y equals x. So it's headed up towards infinity and down towards negative infinity. Well, let's plot some points. Let's set the numerator equal to 0. X times x plus 2 times x plus 1 is equal to a big fat 0. That happens if x is equal to 0. If x is negative 2. Or if x is negative 1. So 0, negative 1. Negative 2. Now we got a bonus because we also happen to get the y-intercept at the same time, because f of 0 is equal to 0 times 2 times 1 on top of 1 which is 0 over 1, which is 0. Score. Now, if you remember multiplicities when you're graphing polynomials, if a factor has an even exponent, it touches the axis. If it has an odd exponent, it crosses the axis. So it's going to cross the axis at 0, at -2, and at -1. You could also think about that same thing we were talking about before. It changes signs. If I plug in something bigger than 0, all of these terms are going to be positive. The output there is going to be positive. If I plug in something between 0 and 1, well, that's going to be positive. That's going to be positive. X would be negative. The denominator is always positive. So that would be a negative thing. If I put in something between -1 and -2, negative, positive, negative. And if I put in something less than -2, negative, negative, negative. So my graph looks something like that. Questions? Okay, I'm going to get this other survey that I have to have you fill out because you have to say whether you learned anything.